third-party FPGAs and things like that. It's quite interesting.
How do I go back and forth?
Just up, down,
Cool. So, yeah, my name's Scott White. I'm a network engineer at Google. I am nervous, so I'm going to do my best here. I don't talk as fast as Tom. I don't use that many words. We'll see how I do. So, what is an open source LSR? What do I mean when I say open source LSR? Of course, the LSR part is fairly obvious. I mean an MPLS label switching router, but I don't mean any more or any less. I mean the part where you do the label swapping. No popping, no pushing, just labeling, only handles labeled packets. In this particular case, we implemented it using LDP and OSPF in the control plane. It has hardware forwarding via 4 1 gig ports. And I think the most important piece here is when I say open source, I'm actually meaning everything is open source. The hardware, the software, it's all available. The source code, you can download it, you can modify it. I think that's an interesting aspect of it. So why build one? A couple months ago, there was discussion on the list, why don't we have an open source LSR? Why hasn't anybody done this yet? And it got me thinking, and I started looking around, and I found that most of the parts already existed individually. We already had implementations that changed the Linux kernel to support MPLS. We already had Quagga stuff that supported LDP. We already had research projects for hardware that could support some of this. So I thought, well, why don't we stick it all together and try and create a foundation that we can use with the open source community to make it into something more interesting, something more broadly interesting to a large set of people. And then to my own end, because I'm in network research now, I thought if we actually had an open source LSR that we could do things with that would enable potentially some very interesting research, which I'll talk about a little bit later on in the presentation. I did want to note that through the years, there have been quite a few software-based routers, open source and otherwise, and they do quite well. But they all have the same fundamental problem, which is they don't have the hardware support. They can't do things at line rate for very small packets, et cetera. And so I worked really hard to try and find a piece of hardware that could do this, and I think we have a starting point. So like I said, so this was essentially a systems integration project. We had a whole bunch of stuff, and then we had to add a little bit to the end. We have the NetFPGA and the OpenFlow projects, which are both research projects hosted by Stanford University. We have MPLS Linux and Quagga LDP, which are both open source projects that have been around quite a while, actually, that modify the MPLS, modify the Linux kernel to support MPLS. And then the piece we had to synthesize was a way to synthesize all these together, and we called that the LSP synchronizer, which I'll explain in detail. So let's talk about each of the individual components, because probably not a lot of you have heard of some of them, or maybe all of them. The NetFPGA is, like I mentioned, it's a research project hosted by Stanford. Its intent is to allow line rate open network research in hardware. It comes on as you can see, it comes on a PCI card. It has a Vertex 2 FPGA, which gives you the bulk of the configurability. It has associated memories to allow you to store packets for queuing and also to create the data structures necessary for packet forwarding. It has 4 gig PHYs and all the associated components for that, and it even has a serial link out the back, so you can actually connect two of these together and get 8 gigabits of throughput. The next component is OpenFlow. OpenFlow is another protocol, or it's another project hosted, research project hosted by Stanford. Its main goal is stated is to enable research and existing protocols to coexist on the same network at the same time. So its intent is to allow hardware to not only support legacy or current protocols, but to support protocols, network research protocols at the same time. It has two basic elements at the highest level. I won't get into a lot of details of OpenFlow, but it has basically a controller and it has an OpenFlow switch. The OpenFlow controller in their model is where most of the smarts live. It makes most of the forwarding decisions. It figures out what the flow entry should be, and then it has an OpenFlow wire protocol that it uses to push down to the OpenFlow switch. The OpenFlow switch in our case is a Linux, it consists of several things. It consists of a Linux module, which is essentially a HAL. It takes the OpenFlow wire protocol, translates it into instructions the hardware can understand, gives that to the driver in the kernel, and then the FPGA driver, which then programs the hardware. I should mention so that was OpenFlow. What we used was the MPLS OpenFlow. MPLS OpenFlow was implemented by Ericsson Research last summer as a research project where they took the standard reference NetFPGA OpenFlow implementation and they modified it to support MPLS primitives, push, pop, swap in the hardware. For this project, we didn't need the full-blown capabilities of an OpenFlow controller, so what we did is that we implemented via the MPLS, the Linux changes, we implemented a kernel LFIB, and then we implemented a mechanism to take the LFIB information, convert it into the OpenFlow wire protocol, and then push it to the standard OpenFlow switch implementation. So what we have here is a kind of a graphic representation of what's going on the Vertex FPGA. Basically, OpenFlow arranges everything into a flow table. The flows are a series of matches and actions. The matches in OpenFlow are basically a tuple of headers in the packet that you can match on to specify the flow you want, and that action can be some number of things to manipulate the packet or change its forwarding behavior. In our case, the way we program the hardware in the flow table, it always matches on an MPLS label, and the action is simply to rewrite, to swap the label and forward it out the appropriate port. On the other hand, if we receive a packet, like a protocol packet, OSPF, LDP, somebody wants to SSH to the box, we need to be able to handle that too. Basically what happens is it doesn't match in the hardware. We have another path through the kernel to make it look to make the NetFPGA look just like a NIC. So basically, non-labeled or IP packets come into the box looking just like they go through the kernel just like a regular packet. The next component we integrated into all this was this MPLS Linux project I spoke about. It basically gave us three separate things. It provides patches to the Linux kernel that basically modify the kernel's Ethernet structure, data structure, so that it can understand MPLS ether type packets. It provided source for building a set of modules, and the kernel modules create all the necessary data structures to support MPLS, things like ILM, NHFLE, the actual LFIB. And then the third thing it provided were patches to the existing IP Route 2 project package. It updated the IP command, it added an MPLS command, and this gives you the ability to either look at the LFIB or actually statically, manually configure things in the LFIB. The last component that we integrated into this that existed was this Quagga LDP. Quagga LDP is pretty tightly coupled with the MPLS Linux project, but what it does is it takes the standard Quagga suite and it adds an LDP daemon to it, and it modifies the Zebra daemon to understand MPLS and the LFIB that's provided by the MPLS Linux project. So we get the OSPF from the standard Quagga, we get the LDP daemon from this project. Specifically, what we used, what we tested were the downstream unsolicited liberal attention and order control. Nothing too fancy. So what we end up with is in the control plane we have Quagga providing the labels via LDP, providing kernel LFIB updates via ZebraD. And then down at the bottom we have the hardware. We have the OpenFlow with the wire protocol, able to program the FIB into the hardware. What we needed was a way to glue these two together, and that's what this LSP synchronizer does. It basically every 300 milliseconds, that's configurable. Every 300 milliseconds, it scans the kernel LFIB, it scans the fib that's on the NetFPGA, and it compares the two. And if it notices that the LFIB is different, it basically generates all the necessary OpenFlow wire protocol commands necessary to update it, and gives those to the OpenFlow switch, which then updates the fib, and we're back to synchronized fib. So here's a block diagram of the system. You have the NetFPGA at the bottom with the picture of the flow table. You have in the middle, you have the NetFPGA driver. The NetFPGA driver, I think this illustrates that it actually, the two modes it has. It has the mode where it talks to the OpenFlow module, or HAL basically, to get commands to actually program the hardware directly. And it also has connectivity through the kernel NIC interface so that it can talk to the standard processes, user space processes. So what happens is LDP gets a packet. A packet comes in, it's an LDP packet, it's not labeled, it won't match anything in the hardware. It goes up to the driver forwards it through the standard NIC interface of the kernel up to the LDP daemon, which grinds on it, gives it over to the Zebra daemon, the Zebra daemon figures out what it is and pushes it into LFIB. And that happens a series of times. And then periodically, the LSP synchronizer wakes up, notices that there's differences in the LFIB. So it scrapes the LFIB and the fib, and then it basically pushes those down into the hardware. And so now for any labeled packet that comes in that matches what's programmed in the hardware, we will hardware switch. We needed to do some basic testing on this. We started by just testing the hardware in isolation. We just hooked up a NetFPGA and a PC2 and Ixia. We really wanted to test just to make sure that we could do line rate in both directions at the same time on a single port at both extreme packet sizes. In our case, with the particular PC hardware we had, we were able to software switch through the kernel about 120 megs per second at 1,500 byte packets plus the MPLS label, whereas in the hardware, we were able to get line rate. And then, as expected, when we go to the minimum size packets, the kernel suffered even more, and we were only able to get about 30 megs a second of throughput through the kernel versus full 1 gig in and out on the hardware. Once we knew the hardware could do the line rate we were asking of it, we had to verify the control plane. And the way we did this was basically we built a small lab, 3 of these open source LSRs as a core, a Juniper M10 and a Redback SmartEdge 100 as LERs. We then enabled OSPF on every router to make sure that the Quagga OSPF implementation interoperated, and it did. And then we added LDP on top of that, and we were able to distribute the labels between all 3 implementations just fine, and we were able to ping to our heart's content. One other test I thought would be interesting would be to just use, again, the same open source LSR core with no BGP in it, just simple labels. Have 2 Juniper M10s acting as the LERs, form an iBGP session across them, simulate a full internet table across them, and then ping the host. And so this kind of just demonstrated to me that there is some potential here to use this in a BGP-free core. Although I focused on, for the purposes of this summer project, basically, how can we get an LSR going? There's no reason why we couldn't make this an LER. The hardware already supports the pop and the push primitives. It's already in there. It's just a matter of getting a bit more software support. Okay, I'm going at like warp speed here, but that's good because we're all hungry. So basically, there's some near-term and medium-term things that I think this could be really interesting for. The near-term stuff, because it's a systems integration and because there's 4 underlying open source projects that are all relatively active, there's quite a few bug fixes that need to get pulled up. One of the hardest things this summer was to pick a kernel version in Linux because none of these worked on the same distribution or the same version or anything. So we picked a version and we got them all working on that. We need to keep moving that forward. I feel after that experience that'll be really that'll be easier if we can get, we did it with 32-bit for expediency. We'd like to get it to 64-bit because a lot of the current development work in the kernel is in 64-bit, so we'll get more support. We'd also like to get this ported to BSD, which shouldn't be too difficult, and that should open up that large community of developers to this project. We'd also like to get some more protocol support in the Quagga stack, things like RSVPTE, better ISI support. That would really make this more useful to a larger number of people. And then probably one of the more important things is we're waiting on, they're in progress, is a 4x10 gig NetFPGA, the next generation NetFPGA card. So we're going to go from a 4 gig LSR to a 40 gig LSR. So that'll make things much more interesting from that perspective. Looking forward a little bit, I think, from the research perspective, one of the things I'm going to do with it is I'm going to take some number of these open source LSRs and centralize them with a single OpenFlow controller, and we're going to research how we can build a small network, whether it's data center or peering edge or whatever, using these devices in that kind of environment. And then I'm also going to continue, I have a lot of interest in trying to, in the lab, develop a BGP-free core that's inexpensive and scales in the data plane so that we can actually figure out how to build one of these at scale. And that's it, really. The tarball is hosted at code.google.com at opensource-lsr. You don't need an NetFPGA if you don't have it. Probably nobody does. You don't need an FPGA to actually test the software piece of it. You can easily get everything working right up to the part where you need to program the hardware. So you can at least have a software-based LSR. And then if you're interested in the underlying projects, I have their repos listed here. It would be very nice if we could get more support in these as well, because if we could, it would just simplify things greatly if we could actually get MPLS support directly in the Linux kernel rather than on a branch. If we could get the LDP support pulled up into the main Quagga branch, it would help. It would not only help this project greatly simplify, but it would help, I think, the whole routing community in the open source sense. That's all I have, really. Any questions?
Danny McPherson, thanks, Scott, for sharing this. I got kind of a two-part question, actually. I was wondering if, I've heard OpenFlow come up in the context. I know this is kind of on the periphery of what you were talking about, but in the context of scaling virtual machines on like a common hypervisor to alleviate some of the link layer traffic, for example, ARP broadcast traffic that might go across a common link layer network attachment, and doing it on the end system that might be at the hypervisor layer, for example. And I was just wondering if you had any thoughts on that, or that as an application for this, or if that link layer traffic might be problematic at all, or if that's not a problem in the environments you're familiar with.
Well, that's a lot of questions. I hadn't thought about it in the context of this. This was really just more of how can we do a straight, simple, basic, what's the most basic MPLS functionality we can start with, and how can we build on it? So I guess I'm not really too familiar with OpenFlow and the hypervisor role you're talking about. I'd like to talk to you about it offline maybe so I can understand it better.
Thanks.
Anything else?
Okay, so if there are no more questions, thanks very much, Scott.